So in our previous video, we were able to build our geometry, and we also added our physics for the work, that the solid mechanics and the secondary current distribution, and we placed in our parameters and variables. In this video, we'll continue from where we left off, where we will be adding our mesh. Let's add our mesh. Okay, so the meshing, what we'll do is we'll be using a free triangular. So under the mesh, we have a free triangular. And we locate a domain selection where we select all domains. Afterwards, so the selection is all domains. So afterwards, we add a size. We also locate the geometric entity, and we'll select boundary. For this selection, we have to specify the exact boundary where we want to select our work. So we also do some little changes at the element size parameters. So we want to change the maximum element size associated with this. So what you have to do is you have to choose custom maximum element size, and it's reduced to this. Then we can build it helps us to get a very small meshing at this side, this boundary. So steady, as we already know, is a stationary steady. I explained it earlier, and we'll be using the parametric sweep for this work. So what we'll do now is we want to select which parameter we'll be working with. We want to select the displacement, and we put in this parameter values here. And this value should be placed there. Tell us this value. And this. What we'll do next is add a second stationary. So we have the first stationary, which under the physics and variable selection, we'll select that for the secondary current distribution. So move on to the second stationary, we select that for the solid mechanics. We add solver, default solver, show default solver. Okay, So we expand the default solver. And the stationary solver too. We want to reduce the relative tolerance here to this value. Okay, so now that we've selected this, now move to the steady. We uncheck this and we can compute our work. After we'll make some plots from this work for the corrosion potential, the stresses, anodic potential, cathodic potential, and several others. It should take some few minutes to finish. So we move to our results and we add to the plot group. The label will be corrosion potential. And fondness, stress. Locate the data set, which should be for the parametric solutions. And we add a surface plot to this. When we locate, we have to find expression for our stress. And also we have to change this unit to MPa. We add another surface. For which the value of the expression should be potential. Okay. Okay, the range. We want to make a manual color range. As this value to this value. Should be a reverse color table. And we make the plot. So afterwards, what we'll do next is to add another plot, 1D plot group for the corrosion defect line. So we add a 1D plot group. So that will be the Von stress. Our data set would be the parametric solution. X-axis is the defect length. Millimeters. We add a line graph to this. And we select those particular boundaries. Inspections at the y-axis will be the stress. Unit as well will also change to MPa. Locate the X expression for the x-axis, make it X, and the units will be in millimeters. Also expand the coloring and style. From the line markers, you choose a circle. Expand the legends. And legends should be manual. So we can input some values. This would be this would be so so after inputting this, what we can do is we go to one misses to plot, and we have this. So now we'll do our plot for the corrosion potential. What we'll do is we just duplicate this and make some changes. And we change this to corrosion potential. Corrosion potential. Y-axis has to also change. corrosion potential move the line graph have to replace the expression for the y-axis, and because it's potential, we're dealing with secondary current distribution. And we select this. Now we can plot so the plot for our corrosion potential, we notice that we have some kind of unusual behavior over here, which doesn't look like the right plot that we're looking for. If you compare this to the von Mises stress, you see that this is the right plot. It's uniform. So the reason is that because of if you look at the convergence plot, you realize that the iteration number or the value, we did not reduce it that much. So that's why we couldn't get a very good plot for that. But for the stress, it didn't really affect it that much. So we want to reduce the relative. Let's go to the side. So remember that we did two stationary studies, one for the secondary current distribution and one for the solid mechanics. And what we did was that the secondary current distribution being the first stationary, when we go to the stationary solver one, the relative tolerance was set to the default value, but we just reduced the relative tolerance for the solid mechanics. So we want to do same for the secondary current distribution and compute before we plot. So after this, we expect to get a better results. It should take a little while. Okay, so now that we are done, let's go back to the plot to check if it has affected it. So alternatively, let's just make it this way. We'll make this, we first do the solid mechanics, then secondly, we do the secondary current distribution. That way it's better, so that it makes our work much easier. So what we'll do is that, okay, so this is the second solver. The first solver, we take it back to default. The secondary current distribution is the second solver, second stationary, and let's compute our work. It should be done soon. Okay, so now you can see that the plot is now in good shape now. As we expected it, it's in good shape now. So if you follow what I did, the first stationary should be the solid mechanics. The second stationary should be the secondary current distribution. And you make sure that the stationary solver for the secondary, this stationary solver 2, the relative tolerance has been reduced. So you just make sure all these things are in line and you get this result as I've done. Okay, so I think we can do some other plots as well. How about we look at the anodic current distribution, anodic current density, sorry. So you can duplicate this corrosion potential, duplicate it. And in the label field, we'll select anodic current distribution. Density, sorry. Y-axis should be anodic current density. And also, let's put in the units. We just have to just put in the units to make sure we're in line. You go to the line graph. You have to replace the expression also for the y-axis. As we did, we go to secondary current distribution electrode kinetics, local current density. So you see we have two types. So we select the first type. And then we plot. So this is another current density. We can duplicate that to plot the cathodic current density. This will just change the cathodic current density. Cathodic current density. Go to the line graph. Solid mechanics. We have cathodic current density. So that should give you the plots for the cathodic current. We have the anodic current. We did the corrosion potential. This is the defect length. We did the corrosion potential surface plot for both the corrosion potential and von Mises stress. So if you have any questions, kindly let me know in the comment sections and I'll do well to respond to that. And I'll see you in the next video. Thank you.